revise smooth sensitivity.
Okay, thank you. So this is based on work with Mark Baum that is like very ongoing. I think we had a bit of a last minute rush to get this talk ready. Okay, so the outline of the talk is I'm going to tell you about smooth sensitivity, as the title might have led you to believe. And in particular, I'm going to tell you about some new algorithms that use the smooth sensitivity framework. But before I get to that, I'm going to sort of set the scene a little bit by talking about a motivating example application of smooth sensitivity, which is going to be Gaussian mean estimation, which is very similar to what Vishesh talked about on, was it Monday or Tuesday? And in particular, I'm going to look at the trimmed mean as a estimator. And then I'm going to apply smooth sensitivity to the problem of Gaussian mean estimation via the trimmed mean estimator. And then I'll wrap up and talk about further work in this direction. And the overall moral of this talk is that we're trying to get a little bit more mileage out of the smooth sensitivity framework, which is this really great idea that I think is a little underappreciated. Okay, so let me start with sort of a motivating problem, which is the estimation of the mean of a Gaussian. So you have data that's IID samples from some Gaussian with unknown mean, and your goal is to figure out what that mean is as accurately as possible. And you know, let's just say some bounds on where that mean lies, and also you know where you know the variance. Just for simplicity, that's not really necessary. Just for the talk, it's easier to assume it's known. And the constraint that makes this difficult is that you must satisfy differential privacy of some flavor. Now, I think this is a really important problem because it's such a basic problem. It's really something we should have solved right at the beginning, and that's why I think it's important to study it. Just one note is that the distributional assumption is only there for utility. The differential privacy assumption should still hold in the worst case for any input. Okay, so let me just sort of preview what the result that we'll get at the end is. So assume that the number of samples is sufficiently large, then there's going to be a differentially private algorithm that takes n samples from a Gaussian, and outputs an estimate of the mean, which has mean squared error, this. So the first term is sort of the non-private optimal mean squared error, so that's exactly what we want. And then you get this additional term, which is the cost of privacy. And you'll see that it's not too large. And in particular, since this is over n squared, for large n, this should be a lower order term. You should be getting basically the right non-private variance plus a low order term, which is kind of exactly what we want. Now this bound basically matches the previous work by Vishesh and Salil that was talked about on Monday. They of course looked at confidence intervals rather than mean squared error, but these are sort of roughly the same. So one thing to note is that this works fine if you have an unknown sigma. You just get some extra terms, and it's also not specific to Gaussian data, so we can apply this to a lot of different distributions. Okay, so how do we do Gaussian mean estimation non-privately? That's a pretty standard thing. You have your data, and your non-private estimator is just the empirical mean, the average of the samples that you've been given. This is unbiased, so an expectation gets you exactly what you want. And it has minimal variance, so that means it matches the Cramer-Rao lower bound. So the problem with trying to just adapt this to the private setting is that it has infinite sensitivity, right? If you take one of these samples off to infinity, then the entire estimator will go off to infinity. So we just can't add noise and automatically get differential privacy. So Vishesh talked about this in more detail, but the one suggestion is truncation. So you first obtain some crude estimate of the mean, just within a couple of standard deviations. Then you truncate the data to some interval, and now you have finite sensitivity, and then you can add noise to that. Okay, so I'll tell you about our approach, which is to use the trimmed mean. So what does the trimmed mean? So the intuition is to basically do outlier removal. So you take the m largest observations, throw them away, throw away the bottom m observations, and just report the mean of what's left over. So a little bit more mathematically, it's a function, takes in n samples, outputs a single one. What you do is you sort the samples, so you get x1 through xn in sorted order, and then you output the average of the samples from m to m plus 1 to n minus m, and you average that because you've removed two m of them. That's the right scaling. So it's a fairly simple operation, but the nice thing is that now a single point is not going to throw things off too much. And my intuition is that this interpolates between the mean, which corresponds to setting m equals 0, and the median, which corresponds to setting m to be as large as possible without making this denominator 0 or negative. And this is unbiased, which is nice. So we have a symmetric distribution. You throw off something from the top, you throw off something on the bottom. As long as you throw off the same amount, it's not going to affect the expectation. And also, turns out it doesn't increase the variance too much. So basically, you get the variance that you would get with the mean times 1 plus some sort of low order term if you think of m as being much smaller than n. And both of these are just corollaries of it being a symmetric distribution. Okay. So just to make things a little more concrete, here's a graph of how the variance changes with m. So if you have m equals 0, that means you're just getting the mean, and that's going to have variance 1 over n if you're looking at data from a standard Gaussian. As you do more and more trimming, the variance goes up until it reaches pi over 2n, which is the variance of the median asymptotically. So why am I showing you this picture? So I can show you the next picture. So I want to emphasize that this is not, trimming is sometimes a good thing. You might even do this even if you're not concerned about privacy. Because trimming can actually reduce variance if the data is heavy-tailed. And one example of a heavy-tailed distribution is the Laplace distribution, which I'm sure you're all familiar with. Now, we don't usually think of this as being heavy-tailed, but relative to the Gaussian, it's a little bit heavy-tailed. And if you plot the same picture, you'll see that trimming actually reduces variance. It's very nice. I think that sort of tells us that we're on the right track with this trimming. Yes?
In that case, I mean, the median is the efficient estimator for the...
Right, so for the Laplace, the median is...
The unique.
Is the maximum likelihood estimator, yeah.
Sure.
But this also applies if you have, say, a mixture of a Gaussian with variance 1 and one with variance 1,000,000, right? So a lot of different settings you can actually be winning from trimming.
You might have a problem if it's not unimodal.
Fun?
If it's not unimodal, if you have a mixture of
Right.
Gaussian with different means and you want to do anything
That's
you want
true.
to understand about them, you'll go banana.
That's true, yeah. So if you have asymmetric distributions, generally these
Even symmetric. Symmetric but two peaks.
Right.
Let's look at the mean.
Yeah, but like,
So we can, that's fine.
very fast with it.
Yeah.
Sorry, if you go back to the last picture, it's going up, going back up, which contradicts what John is saying, that the median is the best. So is it that for any finite n, you want to be a little bit trimming, but as n goes to
I think,
infinity?
yeah, for finite n, I mean, you can see like...
It's the unique efficient estimator in the...
asymptotically as n goes to infinity. I know, I thought this was a cool plot. Like I didn't quite know what I was expecting when I ran. Okay, so let's look at the sensitivity of the trim mean. So we'll assume that there's some kind of bound on the data. This can be a very, very loose bound, A to B. And this means we'll have finite global sensitivity, but it'll still be quite large if we're thinking of B minus A as being pretty large. But what's smaller is the local sensitivity. So if instead of looking at all neighboring databases, I just look at databases that neighbor my current database, the one that I have realized, the sensitivity is much smaller. So basically, the worst thing you could do is either take the smallest thing here and move it up to n minus n plus 1, or vice versa. You could take the largest thing that's left here and move it down to the smallest one, and those are the two terms in the max of the local sensitivity. Okay, great. So that is my segue into smooth sensitivity. Did you have a question? No. Okay, so the idea of smooth sensitivity is really nice. So basically, right at the beginning of the literature of differential privacy, we learned that adding noise proportional to the global sensitivity of a function provides differential privacy. But we really like to be able to add noise that's proportional to something smaller, like the local sensitivity, because often that is a lot smaller. Now, the problem with just doing this is that this local sensitivity itself may be high sensitivity, so the magnitude of the noise you're adding could compromise privacy. So for example, these two distributions have exactly the same mean but totally different variances, and you could probably tell these two apart. Right? If you get a sample from out here, it's much more likely from the blue than from the red. And the solution is this smooth sensitivity, which is a really, really beautiful idea. And so the point of this talk is to re-examine this idea and see if we can get more mileage out of it. Okay, so what's the approach? So let's say we have some function f, that's the function we're interested in. And we also have a second function g. And we have the fact that g is sort of an upper bound on the local sensitivity of f. So for all neighboring databases, f and f of x prime can differ by most g, but also we have some multiplicative guarantee on the sensitivity of g. So on neighboring databases, g can only change by a multiplicative factor. And then we're going to just say that this is g is a t-smooth upper bound on the local sensitivity of f. So suppose we have one of these things. So this is something that's a bit stronger than just local sensitivity. If we have this, then we can use the following algorithm. We take the function f that we want, we add some noise, but now we scale this noise according to g. But obviously the question is, what noise distribution z can we use to make this private? And the key issue is that in order to satisfy differential privacy, we need not just that an additive shift remains indistinguishable, but also that a multiplicative shift remains indistinguishable. So we have to handle both additive distortion and multiplicative distortion. Just a picture, we have this blue, which has an additive distortion over to the red, and also a multiplicative distortion to the green or the orange. I need to make sure that all of these are going to be indistinguishable in the sense of differential privacy. Okay, so there's no unique solution to the right distribution for this. It really depends on various things. So I'll tell you what the distributions in the original paper are. So the first one is the Cauchy distribution, which has density proportional to 1 over 1 plus x squared. And you can sample this by just looking at the ratio of two independent standard Gaussians. And this provides pure differential privacy, but the problem is that it has infinite variance, and even the mean is not defined. The integral for the mean does not converge. Now you can look at a more general distribution where you have a higher power on x, and this is going to still provide you pure differential privacy, but with somewhat worse parameters, depending on that gamma. But now you have your moments up to gamma minus 1. So you have a couple of moments, but not all of the moments will exist. And that's actually necessary if you have a distribution for a pure dp. You're not going to have all your moments.
Question?
Yes?
Don't the first and third bullet points kind of contradict each other? It says provide pure epsilon dp, but then it's net.
So it is necessary for a distribution satisfying pure dp to not have all its moments.
Oh, I see. Okay, I see.
I guess that is the logical implication there is a little confused. And also, they show that you can use Laplace noise or Gaussian noise, but then you have to move to epsilon delta approximate differential privacy. which means you're going to have to pick some delta, and then you're also going to have to pay some sort of log 1 over delta term. Yes.
And if we wanted Renyi?
That's exactly what the next slide is, yeah.
Okay. I'm here for you.
That was a climate question, right?
2007.
Right.
Renyi.
Okay, so I'm going to tell you some new distributions. So the first one is not really new. It's just a slight variation on the one that we had on the previous slide. So this like inverse polynomial thing has a name. If you scale it like this, it's the student's t distribution. This is something that people study all the time, and it's a nice way of sampling it. If you take the ratio of a standard Gaussian with a chi, the square root of a chi squared distribution, that's providing pure dp. Also, a certain number of moments exist. I thought that's a nice observation that this has a name. But let me tell you the first new distribution, which I call the Laplace-logNormal distribution. So basically what you do is you take a standard Laplace, that's your x, and then you multiply it by a log-normal distribution. So log-normal is e to the normal. Multiply these two together, and you're going to get a distribution that's going to satisfy concentrated dp, which is nice. And also it has all of its moments. All of the moments exist. So it's a much better behaved distribution, although again it's a different definition of privacy. So it turns out you can actually do another variant of this, which is what I call the uniform log normal. So instead of x being a Laplace random variable, now it's just uniform on -1, 1. This also has the same guarantees. However, the analysis is not quite as good. And you'll see later. And then we had one more distribution, which was the R-cinch normal distribution, which is you take a Gaussian and then you apply the hyperbolic sine function to it.
This is my first guess, yeah.
Yeah, I know, this is exactly what came to me. So this again provides concentrated dp. It has all of its moments. But the analysis of this, like Mark and I kind of gave up on that. I mean, we have a result, but it's not something we're proud of. Okay, so these are 3 new distributions. I think that's cool. So the one that I want to highlight is this Laplace-logNormal distribution. This seems to be the one that works cleanest of the things we've tried. And I think it's also very natural because, as the sigma parameter goes to 0, you just get a Laplace distribution, which is something we know and love. Okay, so I just wanted to put in a slide about concentrated differential privacy since I've talked about it. Maybe not all of you have seen it. Sort of in one sentence, it's like a best of both worlds between pure differential privacy and approximate differential privacy. You have strong composition results, and you don't have delta, which to me is the best of both worlds. Of course, there's some things that are not perfect, but that's not discussed here. There are, of course, many different variants of concentrated differential privacy, and they all kind of are getting at the same underlying idea, and it's a connection to information theory using Renyi divergences to capture similarity of distributions. And just to put the definition up, if someone hasn't seen it, basically an algorithm has this concentrated differential privacy guarantee. If the Renyi divergence between these two distributions on neighboring data sets satisfies some bound, which depends on the divergence parameter. So you look at all parameters simultaneously. Okay, so I've told you what we're trying to prove about it. I've told you what the distribution is. So now let me just sort of in one slide tell you how we analyze this guy. So again, we take a Laplace random variable, we multiply it by a log normal. And we want to show that it provides concentrated dp when you do it with smooth sensitivity. So here's the theorem statement. Basically, if you look at the distribution of z and compare it to z with both an additive and a multiplicative distortion, you're going to get this bound, which is exactly what you need for epsilon, half epsilon squared concentrated dp. with this value of epsilon. So you'll see in this, this value of epsilon, you have this is the multiplicative distortion. So if you pick larger sigma, you pay less for the multiplicative distortion. You also have this term which is the additive distortion, and you'll pay more for that as sigma gets larger. So there's a trade-off in sigma, yes.
So the Gaussian is normal 0 sigma squared? Oh, no, sorry.
The Gaussian...
These are normal 0, 1, sorry.
Yeah, so it's normal 0, 1, and I just
Sorry.
pulled out the sigma separately.
And the Laplace, we never do it with, we never change the scale of the Laplace.
Well, what we would do is like divide it by whatever we want as the desired s to like get. Because we'll run the analysis and we'll say, okay, well we have this amount of epsilon that we want, we have this amount of
Okay.
multiplicative that we want to deal with. How large can we make s, and then we'll just scale it so that we get whatever the sensitivity of the thing was, we scale it to make that work. Okay, so let me try like analyzing this in 3 lines. So the first thing is that the log normal deals with the multiplicative distortion. So let's just look at the multiplicative distortion on its own, z versus e to the t times z. We can write that out. Now, radiant divergence has this nice quasi-convexity property, which means I can kind of just take out the x. I can say, well, this is, I'm just multiplying both sides by x, so I can just ignore it. I can divide by x, and we're done. So now we have this. And then I'm just going to use the fact that we have the data processing inequality, aka post-processing, to just take logs. So now I'm comparing the Gaussian normal 0 sigma squared with normal t sigma squared. And that's something we all know and love. It's just this, this ratio here. So kind of the idea is that by putting this Gaussian into the exponent, we're just sort of adding Gaussian noise to the multiplicative distortion. Okay, and then for the additive distortion, so we just look at z versus z sorted by s, we're going to get pure differential privacy. So, and so the intuition for this is, well, there's a Laplace in there as well. And that Laplace is giving you something that's going to look like a pure dp with a scaling factor, but don't worry about that. So we just get sort of a pure dp that sort of scales with this s. And then we just need to combine these two together using the triangle inequality, which we generally refer to as group privacy. And we combine them together to get exactly this guarantee here.
Is
Yes.
e to the 3 sigma squared over 2 to the 3 half sigma squared, is that like the expectation of the...
No, it's not. I mean,
Some expectation of some function?
I don't have a good intuition for where that comes from, but it's very generic in the analysis. Like if I do the analysis, I just say x is some distribution. I don't even tell you what x is. I'm going to get this e to the 3 halves sigma squared. So this seems to be sort of somehow inherent to this. Yeah, I don't know where that comes from. But it's not too bad. I mean, if we think of sigma as a constant, it's a constant. Although there's some optimization to be done.
So there you can't use... Quasi-convexity is not enough there because you'd have to take like the maximum over...
Right, so that's the first thing I tried to use like exactly this approach, except now I take the y out. But then I have like something that has log normal here. And it ends up being like in the exponent, and then it's infinite, and it doesn't work. So that was the intuition that we had to sort of get us to properly analyze it. So yeah, so the initial intuition was that we sort of take this thing, do it the other way around, get rid of the y, just deal with the x, and then that deals with the additive thing. Doesn't quite work. Okay, so the analysis of the uniform log normal turns out to be quite similar to this. The same trick here works. You also get pure dp, but the constants are a little bit worse, and it's a little bit messier, and then we apply the triangle inequality. So the other distribution I showed you was the R center normal distribution. The analysis of this is completely different. Mark and I filled up several boards trying to figure out what's going on, and it's still not very good, but we do have a result there. So we conjecture that you can analyze that much more nicely. Okay, so one more thing I want to mention is that we need to look at the tails of these distributions. So all these distributions that I've mentioned to you have tails that are quasi-polynomial. So that means if I look at the probability that my noise exceeds some threshold z, it's going to be something like e to the minus log of z squared. And we get an analogous bound on the moment. So the pth moment of the distribution is going to be something like e to the p squared. So this is necessary, and it's pretty easy to show you to prove a lower bound. This is going to be 3 lines. So let's apply group privacy. So we know that z, the distribution of z, is about the same if I add a distortion of s. Then again, I can do a distortion by multiplicative e to the t. I can do another distortion all the way up to kt. And I have some sort of group privacy saying that this distribution is close to this distribution. So now I can relate the probability that z exceeds this with the probability that z exceeds this quantity here. And if I pick my parameters right, that's just going to be something like z greater than 0, which is a half. And so now that's the parameter I have to set in there, the k, to make that work. And we use some sort of group privacy bound on the divergences. So this is just the KL divergence. This is going to be at most a half k squared epsilon squared. That's just the group privacy bound, following these inequalities through. And you just rearrange that, you write out what this divergence is, and you'll get something that's like p times 1 minus p is greater than e to the minus k squared. So simplifying that, that's p is greater than e to the minus log z squared, which is exactly what we're getting. So there's a lower bound that shows that this is tight. There's no way to avoid these quasi-polynomial tails.
Even if you just wanted KLs.
So this is, we're still applying group privacy here, right? So group privacy blows up the alpha parameter. So even though at the end I'm only going to use KL, I'm going to have to go up to alpha equals k. Okay, great. So yes.
So the exponential blow-up, though, is dependent on the definition of the smooth sensitivity requiring the g function to be satisfied as e to the t thing. And is it possible that there's an alternative way to look at these local moduli of continuity where we don't require this kind of exponential behavior?
That is a really great question, and I've wondered about it. I don't see an alternate, but you could imagine some other kind of condition potentially being in there. So instead of like multiplicative changes, I sort of have changes in the exponent or something weird like that.
Yeah, I don't know.
I don't know. Seems like a thing to play with and try, see if it works. Okay, so that's me telling you about the basics of smooth sensitivity and some new algorithms. So let me apply that to the trim mean. So I'll just remind you of the theorem that I promised you I'd prove, and now I'm going to do that. So again, we're going to have a concentrated DP algorithm M that has this mean squared error. It's the optimal error plus something that's much lower over term times some logs. So again, this matches the previous work by Salil and Vishesh. And it extends to unknown sigma, so you just have to add this extra term that is like a ratio of the upper bound you have on sigma to the lower bound you have on sigma. And this is not specific to Gaussian data. The only thing that I'm using in the proof is that it's symmetric, and you have a good tail bound. Right? So Gaussians have nice tails. If you have like heavier tails, this log might become like a log squared of its Laplace or something like that. Okay, so here's the algorithm. This is just the generic smooth sensitivity algorithm. We have the function f, that's the trim mean. Now we need to pick, and I've told you about which noise distribution z we're going to use, so what I need to tell you about is how do we pick this smooth upper bound on the local sensitivity g. So let's analyze the mean squared error of this guy. And it turns out to factor very nicely. So the mean squared error of this algorithm is the mean squared error of the f, which is the trim mean, plus the variance of the noise we're adding times the expected smooth upper bound g. Okay, so that's the non-private thing. We can analyze that. That has the optimal thing, a little bit of loss from the trimming, and the noise of the scale of the noise is going to be something like 1 over epsilon. So all that remains is to pick this function g and then prove a upper bound on this expectation. Okay, so reminding you what the trim mean is again, and I've already mentioned we have a local sensitivity bound on this. I want a smooth sensitivity bound, and the optimal smooth sensitivity bound is this function here. So we take the maximum over all databases, local sensitivity at that database times e to the minus t times the number of points I have to change to get to that database. And you can sit down and work that out. It has this expression, which is a little bit more tractable to work with. Basically, the idea is you can only move these things basically to the next guy or a couple of steps along by changing one data point. And this turns out to have an n log n time algorithm to compute it. And just a little technical thing, so we have to define what happens when you ask for like x minus 1. That's just going to be the bounds a, and if you ask for x n plus 1, you're going to get b. Okay, so that's the function g. Now let's analyze the expectation of g squared. We can sort of look at all these n squared terms and just pick out 2 upper bounding terms that we want. So we look at the xn minus x1, so that's the maximum x minus the minimum x. And then we have this additional term, which is coming from the b and a, the worst case bounds. But we're not going to see that until it's been downweighted by e to the minus n times t. So if things are Gaussian, we can easily bound this. This is just a union bound, so we get sigma squared times log n. And then we're going to set the parameter m so that this term here basically disappears, or it becomes a low order term. And we'll set the t smoothness parameter to be something like epsilon over 2. So just set some parameters, take a union bound, and we get some bound on this expectation of the sensitivity squared that we can work with. Then we just plug that in, and that's how we get the result. Okay.
So at the end, you're trimming about 1 over epsilon points off each end. Did I understand that correctly?
Yeah, we're trimming about
Or maybe
this many points, right? So this condition up here is just saying we have some points left over. So this is how many points we trim off. Log of
You might say over sigma.
Okay.
And where does the extra log in come from?
That's the maximum.
That's still like the union bound.
X1.
Oh, right.
Can you remind me sigma max and sigma min?
So if I don't know what sigma is, and I just know that sigma is
Oh, you're
between
range.
sigma min and sigma max, then I can I get an extra log term, which is that.
Can you go back one slide?
Yes.
I'm trying to first.
So the point is just there's lots of terms in here, and we'll just like pick 2 terms that upper bound all of them.
No, I'm trying to figure out, like, the first bound is for any data set, right? Because you're considering privacy, so you should hold for any neighboring, not just neighboring coming from a Gaussian. So I'm just trying to figure out where you're plugging in the Gaussian.
Oh, so yeah, so this expectation shouldn't be here. This works for all x. Yeah, there's no randomness in this one. The randomness
do
comes
x
in.
squared given x.
Yes.
Conditional expectation.
And do you think the log n term is necessary for,
For if you
I mean,
hope.
like on this slide, is it necessary?
Yes. So if you're planning to only trim off like less than n points, by which I mean like n to the 1 minus epsilon, then like you're not going to win at more than a constant factor by looking at something in between. But if you are planning to chop off like a constant fraction, so I chop off 10% all the time, I take n to infinity, then you're going to do better. You're going to avoid the log.
But then you'll paper it in the variance of the trim mean, right?
Yes. So there's a trade-off. If you take off too much, the trim mean costs you. If you take off less, then you're going to have this log n. I don't know which is the right thing to talk about, but I thought this was the cleanest way to write the result.
But did you try like optimizing for n? Like if you trim more, it would reduce this term potentially?
So this setting parameter seems to be optimal for the Gaussian at least. But you could imagine that you have like a heavier tail distribution, and you would want to chop off a constant fraction of Gaussian. Yeah.
I guess empirically you could use the top expression rather than just using this upper bound.
Right. So I mean, we do use this empirically,
And do you know how off it is from just using this screwed upper bound?
I didn't calculate that, but I do have some like graphs coming up, so you can kind of see what's going on. Okay, great. So this is the theorem that we proved. Yeah, as Adam was getting at, there were lots of trade-offs here, so we could avoid this log n, but then this term will become larger. Depends on how this epsilon versus epsilon squared matters. So there's trade-offs here, and I mean for Gaussian data, I think this is the right thing. But the question is, if you have different distribution, what would you want? What would things look like? Okay, great. So getting towards the end of the talk, I want to just sort of show you some graphs. So I did some basic experiments. There's nothing fancy here. So let me give you an interpretation of this. So here's a bunch of different noise distributions that I've talked about. So this is the Laplace-logNormal, uniform log-normal, students T with 3 degrees of freedom, which is the degrees of finite variance. This is just the trimming with no noise. And this is what would happen as if you just use global sensitivity, which would be kind of useless. And here I've got 200 data points, and I'm assuming some sort of bound on the range of 50 to 150. It's standard Gaussian noise, so sigma equals 1. And what I'm plotting here is the excess variance that you get relative to just the non-private optimal thing, which would be 1. So this line 10 to the 0, that means you have 100% more variance, or twice the variance that you would have privately. As you can see, we're getting under that line. And down here, this 10 to the minus 1, that would be like 10% more variance than you're getting on privately. So the kind of annoying thing about sort of writing up a comparison, like an experimental comparison between these, is they all satisfy different privacy definitions. So I'm not entirely sure what the right apples to apples comparison is. So some of these are concentrated differential privacy, and this one is pure differential privacy. And then of course the question is, what happens if we want to compare to the other things like approximate differential privacy? So I also have that graph. So this is the same thing, but now I've added in Laplace, which is going to satisfy 1 10 to the minus 6 differential privacy. And I've added in Gaussian, which will satisfy a different version of concentrated dp called truncated concentrated dp.
Which curve is that? I'm having trouble matching with
So the black one is the truncated CDP one. So this is doing pretty well. You can see the Laplace-logNormal is the best curve, other than this non-private one. The student's t is pretty close behind, so like there's not that huge improvement. But the uniform log normal, I mean that really sucks. This is not. So obviously we need to improve that analysis. And then the Laplace with epsilon delta dp, that seems to be doing really poorly. And maybe there's some more squeezing the analysis to make that better, but it does seem that delta is, if you need to pay for a log 1 of a delta, that really does hurt you.
And you're not getting any benefit out of it, of using a thin tail distribution, because you're just looking at variance.
Right. Yeah, so variance is probably not the right comparison point if I want to highlight the fact that some of these have heavier tails than others.
Yeah. So this, your vertical axis is the variance, just
it's the variance times n minus 1, which is like subtracting off the non-private variance. Mm-hmm. Initially I didn't have this minus 1, but then everything just like collapsed into 1.
Wait, they collapsed into 1, but some of them are at 1,000 and some of them...
For this for n equals 200, I have plots that go up to like n equals 2,000, and then...
Can we see one?
Yes. So this is n equals 500, so everything else is exactly the same. I just have larger n. I haven't said what the horizontal axis is. So this is the amount you're trimming. So over here you're just getting the mean. Over here it's the median. So the data is a little noisy because I only ran these experiments this morning and I didn't have time to do more than like 1,000 repetitions. But at some point I'll have less noisy plots. So you're seeing there's some sort of trade-off. So over here the sensitivity is high, so you're adding a lot of noise for privacy, even though the trim mean is doing very well. And over here you're probably losing more from the trim mean because higher variance. Plus also, I guess, the smooth sensitivity also starts going up at some point. So there's a sweet spot in the middle that you need to look at. So this is n equals 500. This is n equals 1,000. And you can sort of see that these things are getting kind of squished together. So what we're seeing is that indeed the the trimming is what's dominating in terms of the arrow over here. And then I think one final plot, which is instead of varying the trimming fraction, I vary n. So here's n equals 10 up to n equals 1,000 or 2,000. And I see all of these things are going down, which is the right direction. But some are going down faster than others. But yeah, for like n equals 1,000, we're getting pretty reasonable results. Maybe these epsilons are a little too large, but I think these plots are encouraging. Okay, so just wrapping up. Smooth sensitivity is great. I hope I've convinced you of that. How many of the authors are here? 1, 2, 3. Okay, they're all here, so I'm sucking up to the right audience. The contribution here is that we have some new distributions that you can use with smooth sensitivity. They seem to be pretty cool. They have all their moments, which is a reasonable thing to expect. And I think the application of Gaussian mean estimation it's neat. It's sort of a very natural problem and something you would expect us to do. So in terms of further work, obviously sharper upper and lower bounds for this specific problem. I think the analysis I showed you, it does not look very tight. It would be kind of nice to get maybe the constants in the second order terms. It's not very, doesn't sound very exciting, but something nice here. Obviously moving to arbitrary distributions rather than just Gaussians. We have some results in that direction. Everything does seem to sort of generalize fairly well, but it would be nice to have the right results there. And of course, other applications of smooth sensitivity. I think this is an idea that needs to find more uses because it's cool and it's underappreciated. So sort of other things that you could look at is like scale estimation. So what if you also want to know what sigma is? Can you do that? And I have some ideas for how to do that. Confidence intervals, this is what Vishesh was talking about on Monday. And of course, more complicated things like regression or model fitting. I feel like these should also be able to fit into the framework. And of course, we could have asked for other noise distributions or better analyses of the ones that I have. So in particular, the uniform log normal, I feel like this should have a nicer analysis, but I don't have it yet. Okay, that's it.
Questions?
So when I did various back of the envelope calculations a long time ago, it seemed that in these types of situations, the smooth sensitivity scaling with epsilon was like not that great. So it would be something like 1/epsilon squared, and as epsilon got really small, I'm trying to remember, because there's some trade-off, right? Because as epsilon shrinks, you're smoothing more, and so you pay for that.
Right.
And I was just wondering if you kind of dug into that.
Yeah. So one of the things that I kind of like about these distributions is that there's a sigma parameter that I can
You can
make it larger, and I have some
Right.
trade-off with the smoothing parameter and the epsilon.
And but you said you set sigma equal to epsilon.
So for the plots, I numerically optimized sigma.
Okay.
It came out to like 0.3 for most of the parameter settings, so small does seem to be the order of the day. The other problem is that you're paying exponentially for the additive side, so it's not super
Right. Right.
So, in terms of the dependence on like the boundary you have on sigma, for CDP at least, is it tight? Is your bounds tight?
I would think so, but I don't have a lower bound.
So do you think like we have to resort to sort of PQR if
Actually, I'll take it offline. Sorry.
Okay. I think I may have gone over time, so.
Yeah, that's fine.
Okay, next speaker.